So, hello, Maddie. Um, this probably won't be called Theorem 3, but what I wanted to talk about, probably Theorem 2 in your talk. Um, this is sort of an easy thing to add on um, so that you can, um, after you've talked about the 2PL model and proven those three things about its properties, where the inflection point is and etc., then you can say that item information, talk about its role in item response theory, and this is how it's defined for dichotomous items, which are the kind of items that we're considering. These could be free response or multiple choice. So this is how it's defined, and we want to show that for the 2PL model, it takes on this form. So we're going to kind of walk through that in this lecture. And first we need this lemma. So the lemma is here. And so the first thing I would do is find the derivative of this function, because that's what we're going to try to show these two are equal. So we have e to the dA theta minus b over 1 plus e to the dA theta minus b. Now you probably won't be doing all this in your talk, but in case you need to, here's a way that's easy, I think, to do it. Call this function f of x and call it e to the alpha x over 1 plus e to the alpha x. And alpha will equal dA and x will equal theta minus b. I wrote d, didn't I? So this works because when we take the derivative, we do have to consider the chain rule, but the derivative of this inside function is just 1. In other words, the derivative of x is 1. So we can do this, and it helps us look at the derivative. So I have, this is much easier to see without having to write all those other parameters. That will be squared in the denominator. And then just from good old calculus, we use the quotient rule. That's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. And now we just see how this works out. So I will multiply this out. I get alpha e to the alpha x minus alpha times e to the alpha x squared. This is a plus, my bad, plus minus alpha times e to the alpha x squared all over 1 plus e to the alpha x squared. And you notice you get this nice cancellation. So I can see what my derivative looks like. It looks like dA e to the dA theta minus b all over 1 plus e to the dA theta minus b squared. So there's my derivative. And that's kind of a quick way to derive it if you need to on the spot. Now, let's try to show that that is equal to this. Okay, so first we need to look at what Q looks like. Q of theta. Well, this is 1 minus P of theta. If you want to do it sort of a quick way, Q of x is 1 minus P of x, say. So this will be Q of x equals 1 minus, using this form again, e to the alpha x over 1 plus e to the alpha x. You get a common denominator here, so I'd have 1 plus e to the alpha x minus e to the alpha x all over 1 plus e to the alpha x. This goes away. So now I see that Q of theta looks like 1 over 1 plus e to the dA theta minus b. So there's Q. Here's P. So now, if you look at this, you can almost see it. We're talking about dA times P times Q. So let's just make sure that's clear. Okay, so I have my derivative looks like this, and I'm going to show that this is the same thing as here. This would be dA times, let me go down where I have some more room. I'll write it here. dA times P, which is e to the dA theta minus b over the same denominator, and Q is here. So yes, these two are identical. So this is what the lemma tells us, that P prime of theta can be written as dA P of theta Q of theta. So now that makes showing this in theorem 2, I'll call it. Now we are ready to show this. So let's, well, I think I have a blank page next. So we want to show, well, first of all, let's talk about item information. For dichotomous items, item information takes this form. It's the derivative of P squared over P of theta times Q of theta. Now you should say in your talk in Math 485, you will show where this comes from. Or you will derive, say I will derive this form of information. Now this is for one item, but writing all the subscripts becomes tedious. So when we start doing things, I usually leave the subscripts off. So for now, we're saying that we know that this is what it is, and we want to show that for the 2PL model in particular, this is for any dichotomous items. We have the 2PL and the 3PL that we talk about. For the 2PL model, item information looks like d squared a squared P of theta Q of theta. And this is important. Why? Because once we've shown this, you can talk about the role, in particular, that discrimination plays. So there's the discrimination parameter. So when A is high, information is high. And we can also look to see when is it maximized? When is item information maximized? So we'll talk a little bit about that too. But this theorem is really easy to prove. So this is sort of, I'm not going to do it real formally, but this is what I would say. From the lemma, we have P prime of theta equals dA P of theta Q of theta. And then all we have to do is substitute. We're going to substitute into here. So we would have item information equals this squared. Well, maybe I'll write it again just so we're clear. This is going to be squared, and it's divided by P of theta Q of theta. You can almost just see it right now. So this will be d squared a squared P of theta squared Q of theta squared over P of theta times Q of theta, which equals d squared a squared P of theta Q of theta, which is what we wanted to show. So you see how short that can be. Whether or not you prove the lemma depends on what you want to do in your talk. If you want to do this, you could do it relatively quickly if you practice it, and I would suggest using the alternative form so you're not writing so many little things on the board. But so make a decision about that. But at the very least, I think you should prove this, and then afterwards say something along these lines. Things to note. Item information will be higher when the discrimination parameter, you're not writing all this on the board, you can talk about it and point to things. When the discrimination parameter A is higher. So you can look at this and say, from this form, it is clear the role the discrimination parameter plays in item information. So you can just say, there it is, A squared. What is not so clear is the role of the difficulty parameter. Well, for that, we can look to see where is item information maximized. And these are all things that you should include in your paper. And how much of it you include in your talk will be sort of up to you. But I thought we'd go ahead and look at how do we maximize this function. Well, we're looking at this form of it. Whoops, left off my squareds. Now, this is not going to play a role in the maximization. We will find the derivative and set it equal to 0 to find the maximum. So I'm going to look at, let's just call this function, maybe I'll call this function g of x. This is going to equal e to the alpha x over 1 plus e to the alpha x squared, which is just substituting again alpha equals dA and x equals theta minus b. So find the derivative of g. So g prime, we did a long bar, over, this will be over 1 plus e to the alpha x to the 4th power now. And again, this is just calculus, it's the quotient rule. So what would we get? Well, I'd get alpha times e to the alpha x times 1 plus e to the alpha x squared minus the derivative of this denominator, which is 2 times 1 plus e to the alpha x times the derivative of the inside function, alpha e to the alpha x times f e to the alpha x. Now that's what we want to simplify. So let's do that on another page. Okay, so what does this look like? Right away, I see that this is going to cancel. This exponent will become a 1, and this exponent will become a 3. Does that make sense to you? We have this factor here, and here, and here. So now, in my denominator, I have 1 plus e to the dA theta minus b cubed. And in the numerator, I'm going to multiply this out. I will get alpha e to the alpha x plus alpha times e to the alpha x squared minus 2 alpha e to the alpha x squared. And then we notice that I have one of these and I'm subtracting off 2 of these. So finally I can write this, well, almost finally, as alpha e to the alpha x minus, wait a minute, yeah, that's right, minus alpha times e to the alpha x squared over 1 plus e to the dA alpha minus b cubed. Now this is a little awkward to deal with, so I'm going to rewrite it. I don't know why I'm doing that. Let's do this alpha x so that we're not confusing ourselves. Okay, So how could I make this easier to look at? Well, I'm going to factor out one of these. Whoops. Factor out alpha e to the alpha x, and that will leave a 1 minus e to the alpha x. You multiply that back, and that all looks good. All right, so now we're ready to set this equal to 0 and see when it's maximized. Okay, so what did I do here? I went back and added on my d squared a squared to here. So remember, alpha equals dA. So now I have d cubed a cubed, and then I substituted for alpha dA and for x theta minus b to see that this is what the derivative of the information function looks like. And if you want to include this in your talk, you could just provide it to talk about, and you don't have to derive it during your talk because you don't have a lot of time, but it gives you a way to talk about when is item information going to be maximized. And you can say that it would be in the development would be in your 485 paper. Or it might be something you decide to include in your talk. But anyway, let's talk about how this could equal 0. Now, this denominator, which actually has got a typo in it again. I keep doing that. Plus, plus, plus. Okay, just messed it up there. This denominator is what? It's never 0. So this is strictly positive. D cubed A cubed is strictly positive. So the only way this will equal 0 is when 1 minus e to the dA theta minus b equals 0, or to solve this is very simple. This can only happen when theta equals b, and this keeps popping up. So this shows that we need the difficulty levels. You need item difficulty to kind of match the ability distribution. So that means in general, you don't want too many items with difficulty b equals 3 or difficulty b equals -3. You want most of yours in the middle range where most of the people are. And that's where you're going to get most of the information. And just as an aside, this is not the case in classical test theory. There, it's kind of hard to explain now, but it has to do with the standard error of the estimate. There, the error is highest in the middle range of the ability, and your better accurate estimates are at the low end and the high end, which is not really useful. We'd rather have more information where most of our people are. So anyway, I hope this helps. You need to practice your talk, and maybe we'll talk tomorrow. Um, and I'll tell you what I need you to do about your talk. So that's all for now. I hope you're well. Bye.